Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss vapor lock and heat exchanger flooding in steam systems. The interaction of a steam reboiler with its condensate collection system can be very simple or very complex. Simple in the sense that the plant operators are satisfied to drain the steam condensate to the sewer from the channel head of the steam reboiler or feed preheater. Complex if the operators are trying to route the condensate back to the steam generation or boiler house for recovery and reuse. In many refineries, the ratio of fresh BFW, boiler feed water, to steam generation is so high, 70 to 80%, that one has to wonder, what has happened to most of the steam condensate? Mainly, due to design errors, the plant operators have been forced to divert the condensate to the sewer. Function of the steam trap. The purpose of the steam trap, as shown in this picture, is twofold. 1. To preserve the condensate seal. If steam blows through the outlet drain nozzle on the channel head, the rate of heat transfer will drop dramatically. 2. To minimize condensate backup. If condensate fills up tubes, then those tubes are unavailable to condense steam. Thus, the rate of heat transfer will drop in proportion to the tubes filled with water. The steam trap is designed to pass liquids, H2O, and retard the passage of vapor, steam. There are two problems with the use of the control scheme shown in this picture. First, steam traps are mechanically unreliable. Second, as valve A closes, the pressure in the lower half of the channel head may briefly fall below the frequently unstable pressure in the condensate collection header pipe. When this happens, water in the condensate header could flow backwards into the channel head of the reboiler and rapidly submerge many of the tubes. We would ignore this problem if the steam pressure is 100 psig or more and the condensate collection header is 30 psig or less. For smaller steam flows, 5,000 to 10,000 BTU per hour, we would use a steam trap. For larger steam flows, we would use a condensate pot and level control valve, LRC, as discussed in the following section. The steam trap neither aids nor retards condensate drainage, unless it is mechanically malfunctioning, meaning it is sticking either open or closed. Also, replacing the steam trap with a condensate drum and LRC also neither retards nor aids drainage. Condensate drainage is a function of system hydraulics. Non-condensable venting. There is always a small amount of CO2 in steam. It originates from residual carbonates in the BFW. Compared to steam, the CO2 is a non-condensable with a limited solubility in H2O. As the steam condenses, the few ppm of CO2 will be trapped on the steam side of the tube bundle inside the channel head. However, none of the CO2 will be trapped above the pass partition baffle shown in this picture. And all of the CO2 will be trapped below the pass partition baffle. Therefore, the problem is that venting from valve C in this picture will vent off steam, but no CO2. To purge the accumulated CO2 from the tube bundle, vent valve B must be used. If this non-condensable is not removed from the channel head, then you will observe over a period of days, not hours, of progressive loss in heat transfer capacity. The proof that this is a buildup of non-condensable is that briefly blowing the condensate seal restores heat transfer capacity. The CO2 increases the tube side heat transfer film resistance, rather similar to a temporary fouling deposit. We call this vapor binding. The standard is to continuously vent 0.5% of the steam through a restriction orifice to purge CO2. Even if you are producing steam from demineralized water, just a small fraction of this rate of venting is required. Corrosive steam. If CO2 is not vented off from valve B, then it will begin to dissolve in the condensate to form H2CO3, carbonic acid. This acid causes tube failures due to acidic corrosion. Venting gas below the pass partition baffle will stop this corrosion. Condensate drum. There is no process reason to use the condensate drum shown in this picture rather than a steam trap. In a modern refinery with large steam flows, the convention is to design systems with condensate drums for mechanical reliability. The balance line shown is required to maintain steam pressure in the condensate collection drum. The natural tendency is to maximize the drum pressure to promote condensate drainage from the drum by keeping valve C open and B closed. Then the pressure in the condensate drum would be 40 psig. But the pressure in the lower half on the channel head would only be 35 psig. You can assume a 5 psi delta P on the steam side. How can water at a pressure of 35 psig flow into a vessel at 40 psig? The only possibility is condensate backup equivalent to 5 psi. 5 psi times 2.3 feet divided by psi equals 11.5 feet. Which is ridiculous, as the reboiler is only 5 feet in diameter. Even a 1 psi delta P would submerge half the tubes with water. The operators will respond to this design error by draining the channel head directly to the sewer. Thus, the correct balance line connection location to use is through valve B and never valve C. That is, leave C closed and B open. Condensate drainage and vapor lock. As steam condensate flows through process piping, it loses pressure due to frictional losses. Alternately, condensate draining from a reboiler outlet nozzle will accelerate and lose pressure according to this formula. Pressure drop, PSI, equals 0.015 V square, where V equals feet per second. For example, condensate draining through a nozzle at 10 feet per second would undergo a delta P of 1.5 psi. As the condensate is presumed to be draining out of the reboiler at its saturated liquid temperature or boiling point or bubble point as it loses the 1.5 psi, you might think it would have a tendency to partially vaporize to steam. But this is not the case. Let's say I have 100 psig steam condensing to water at its saturated liquid temperature of 320 degrees Fahrenheit. If 1 cubic foot, about 59 pounds, of this water is turned into steam, it will expand to approximately 150 cubic feet. The resulting increase in velocity will exponentially increase the pressure drop, which will largely choke off the flow. This is called vapor lock. To the operators, it appears as if a valve has been partially closed in the drain line. Depending on the line velocity and length, the flow will be reduced a lot or a little. For a short, oversized line, the effect may be minimal. But for a line sized for flowing water only, at a design velocity of 8 or 12 feet per second for a length of several hundred feet, the effect will be extremely large. Effect of vapor lock. The consequences of vapor lock on the performance of a vertical thermosiphon steam reboiler, with steam on the shell side, is shown in this picture. The boiling point temperature of 60 psig water is about 270 degrees Fahrenheit. The condensation temperature of 100 psig steam is about 320 degrees Fahrenheit. As the condensate flows out of the shell side of the reboiler, it loses 2 psi through the nozzle, plus 38 psi through the condensate drain line. To suppress the evolution of steam in the drain line, the condensate must be subcooled from 320 degrees Fahrenheit to 270 degrees Fahrenheit as it leaves the reboiler. This can only be accomplished by condensate backup. And if the condensate is not subcooled to 270 degrees Fahrenheit, then the condensate will begin to vaporize, which will then A. Choke off the flow, B. Back up the shell side water level, C. Cause the condensate to be subcooled, so that when it falls to 60 psig, it is cold enough so that it does not flash, and vapor lock is suppressed. The problem with condensate backup and subcooling is the very low heat transfer coefficient, U, for subcooling versus condensation. Typical heat transfer coefficients BTU per hour per square feet per degree Fr. Steam condensation equals 400 to 600. Subcooling equals 20 to 40. To condense a pound of 100 psig steam requires 920 BTU of heat removal. To subcool water from 320 degrees Fahrenheit to 270 degrees Fahrenheit requires 50 BTU of heat removal. We can conclude that around half of the surface area of the Reboiler shown in picture is devoted to subcooling, but only for 5% of the Reboiler duty, that is, 50 divided by 920 plus 50 equals 5%. Design options to mitigate vapor lock. Option 1, double the surface area of the Reboiler. Option 2, increase the size of the condensate drain line by an order of magnitude. You can do this, and it will work. However, in general, this is not a cost-effective option for longer condensate collection drain lines. Option 3, inject cold water into the condensate rundown to suppress vaporization. To suppress vaporization of 320 degrees Fahrenheit condensate, as shown in this picture, enough 70 degrees Fahrenheit water, that is, 25% of the condensate flow rate, would have to be injected. This will also give good results. Option 4, drain condensate to the sewer beneath the Reboiler. This unfortunate option is, by far, the most usual solution. Option 5, install a condensate pump and condensate drum. Pump the condensate out under level control. The drum must be immediately next to and underneath the Reboiler. Also, the drum must be high enough above the new condensate pump to provide sufficient net positive suction head, NPSH, for the pump. This is, of course, the preferred, if not the typical way of handling this very common design problem. Elevated condensate collection drum. This picture illustrates a condensate drum that is elevated above the Reboiler steam trap. For simplicity, let's assume that 15 psi of pressure, that is, 1 atmosphere, equates to 35 feet of hot water head pressure. Note that the steam supply pressure is 150 psig with a saturation temperature of 360 degrees Fahrenheit. Assume that the condensate drains from the Reboiler as saturated water, 150 psig and 360 degrees Fahrenheit. The delta P through the steam trap is 0. The hot water will lose 70 feet or 30 psig of pressure as it rises up to the drum, which operates at only 60 psig. The excess delta P above the minimum required is then 150 minus 30 minus 60 is equal to 60 psi. Thus, superficially, it appears as if the condensate could easily flow up into the drum. But it will not. The problem is that the condensate rising from the steam trap will begin to lose pressure due to the gain in elevation. As it rises above the Reboiler level, the hot saturated water will start to flash, undergo vapor lock as described previously, and thus choke off the flow. The condensate will back up in the channel head of the Reboiler shown this picture and become subcooled enough to suppress steam evolution until the condensate enters the drum. The required subcooling may easily floods half or more of the surface area of the Reboiler. The loss of Reboiler capacity typically will not be tolerated by the plant operators, who will then be forced to drain the valuable steam condensate to the sewer. The design of a steam condensate collection system is a complex task. It cannot be approached just as a problem in hydraulics, because it is also a problem in vapor-liquid equilibrium and in the conversion of sensible heat to latent heat. Considering these three factors together requires quite complex calculations, for which we have had to rely on the use of a computer model. These same sorts of considerations apply to multi-component hydrocarbon systems, such as propane-butane refrigeration loops, but then the calculation complexity increases by an order of magnitude. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.